So I'm going to try and say something about the BFO account of information entities. And you'll notice that we don't have a BFO account of information. Information is a mass noun. And what that means is that you can't say two informations or three informations, just as you can't say two luggages or three luggages. So in the case of luggage, you talk about two suitcases. In the case of information, you talk about two information entities or two information artifacts or two pieces of information. And the reason why we make such a fuss is that if you use mass nouns in ontology, you will usually make mistakes. So we just veto the use of mass nouns. So how does BFO deal with information entities? Well, we've already seen the distinction between continuance over here, which we won't be worrying about. Continuance over here and occurrence over here. We won't be worrying about occurrence for what I have to say next, at least not much. And then we have independent continuance, which are things like hard drives or computers or people or planets. And then we have specifically dependent continuance, which are things like qualities and roles, which we already talked about. Then we also have, but this is where information entities come in, generically dependent continuance. Now, the feature of information entities which distinguishes them from things like qualities or roles is that they can migrate from one independent continuant bearer to another. So if I copy a PDF file from my laptop to your laptop, or if I send an email from my laptop to your laptop, then the very same information entity starts in one place and moves to another place. That never happens with qualities or roles. If you become a professor, you do not inherit my professor role. Even if I cease to be a professor on the very same day, you get a new role. So you can't move specifically dependent continuance from one bearer to another. That's what we mean by specific. So generically dependent continuants are those kinds of dependent continuants which we can think of as patterns, very, very roughly, which can move from one bearer to another. That seems to be a characteristic of information. It's not just information entities which can move, also gene sequences can move. And some people call them information for that reason. Bioinformatics is a science which deals with gene sequence information. But BFO would not regard the patterns of molecules, which people call gene sequences, as being information entities. Rather, the information entities are the chemical formulae, the lists of chemical identifiers which map exactly represent the corresponding sequences on the sides of the molecule. So we have at least two kinds of copyable entities. One are information entities, and the other are sequence entities in molecules. Some people think that chemistry is the only science in which names exist in reality, that the things in reality are their own names. That is, of course, nonsense. Chemistry uses names just like any other science. It's just that chemistry is able to name things with exact precision very easily because we have chemical formulae. So we have chemical formulae and we have patterns in the world. We have other kinds of information artifacts. And then we have the patterns in the world, the configurations of independent continuance and dependent continuance and processes which those entities in the world form. So GDCs, this is as far as BFO goes. And we're interested in now in information entities, which are a special kind of GDC, and they're outside BFO because BFO only deals with what is absolutely general. And the question that we're going to try and discuss now is, what kinds of information entities do we have in the world of industry? And of course, we have very many kinds of information entities. We have specifications, we have requirements, we have regulations, we have designs, we have process specifications, work plans, bills of materials, there are work orders, transport delivery notes, and so on. We have many kinds of information entities. So let's concentrate on one kind. Let's concentrate on designs. So a design is an information entity, and information entities now include both information entities on paper, so old paper blueprints, and they include information entities in digital form. Now, there are different ways of treating those different kinds of information entities, but we're not going to be concerned with that. Let me just say a little bit about how we conceive information entities in this general way. Let's just think about a sentence, and we'll have two kinds of sentence, but we'll deal with them separately. So first of all, let's think about a sentence printed on a piece of paper, which is part of a printed book. Then we have the sentence. Now, this is a dependent continuant, and the dependent continuant always has some independent continuant, which is its bearer. So at one level, the bearer of the sentence is the book. So if you destroy the book, you destroy the sentence. That's the characteristic of dependence. Dependence means dependent for your existence. This sentence ceases to exist if you destroy the book, but that's not quite right, because there are many copies of the book. And so in the sense of sentence, which means this particular pattern of ink on this page in this book, if you destroy the book, you destroy the sentence. But that is a sentence in the sense of ink pattern. And we're talking about the sentence as a generically dependent continuant, and that survives. So there is the page of the book, of course, and then there is the ink pattern. So it's a pattern in little piles of ink. And the bearer, in the narrow sense, the strict sense of this information entity, is the tiny piles of ink which have a certain pattern. The pattern is a quality in BFO terms. So there is the ink pattern lump, or I mean the actual ink with.
I think cannot exactly exist without book, right? That's why.
Yeah. If you destroy the book, you destroy the ink. But then there is the ink pattern quality. This is not made of ink. This is a quality. It's a shape kind of thing. It's a kind of quality. It's an ink pattern quality, which is the quality of a certain lump, a certain set of piles of ink. So let's say piles. And that is the bearer of the sentence in the narrow sense. Now let's do the same performance. Well, I can keep this. Now we're going to be talking about not the ink pattern, but the digital pattern.
Question.
Yeah.
Why do we have this direct link from sentence to the book? Why don't we have to this other chain?
Oh, so why do we have what?
Why do we have this link here? Wouldn't we have this link to these? So wouldn't this belong to this one and this one, and also this is.
So the whole point about this is that even if we destroy this, it survives. So we have this relation. This is a specific dependence. This is generic dependence.
But is there a link between this and this?
Yeah, this is called concretizers.
Okay.
All of these are relations in BFO.
Yeah.
So this digital sentence is concretized by this ink pattern, which is specifically dependent on this ink pile pattern. It's a pattern of piles, which has this ink pattern quality. And
Okay, my thinking was just,
Yeah.
can we define this generic dependence to this
yes,
chain?
absolutely.
That's
Absolutely.
what we do. So
Yeah.
we destroy this one, we are destroying this link, but we're
Yeah.
not destroying this because the other
Yeah.
one,
Yeah.
the other copies exist, other copies of the book.
Yeah, exactly. And now let's do the digital case. So now we have, instead of an ink pattern, we have a pixel pattern, let's say,
Okay.
and this is a quality, and so we'll simplify a little bit. So we have a pixel. Now what we need over here is not a pixel pattern, it's the pixel so there is a certain, we're talking now about the laptop, and specifically we're talking about the screen infrastructure of the laptop. And there is a pixel part of that screen infrastructure. That is to say, it's the part of the screen infrastructure which the pixels are a pattern in.
Yeah.
So this is a fiat part. Just as your visual system in your head is a fiat part of your body.
Is this pattern of ink in the book? Is it
It's
also
analogous to it.
Is it also fiat? Ink pattern on the book is.
It depends on the precise details of the chemistry joining the ink to the paper. All right, so this is the basic story. And now let's go back to a design. So we've talked about sentences. Let's talk about a design. And let's suppose the design is a digital design. So we can inherit all of this. Now, of course, a digital design, I'm assuming, is not going to be encompassed in any single pixel pattern. It's going to be much more complicated than that. You can zoom into specific aspects of the design. You can turn it in space, as it were.
Digital design, we're talking about the 3D model of part of product.
So a 3D model. It is not simply a single pixel pattern as contrasted with a sentence on a screen in an email, for instance. So we're not talking here about a pixel pattern. We're talking about something much more complex. So it's a software pattern. And it's going to be not in the pixel part, the screen infrastructure of the computer. It's going to be in the operating part of the computer. It's going to be installed in the computer. And so that you have the place where software is installed on the computer, there is a certain part, fiat part, which is occupied by the CAD software. And a part of the memory which is occupied by the specific design that you are dealing with in your 3D model. So I am now exhausting my capacity to describe where CAD designs live inside.
It's good. We can go. This could be preparatory work for tomorrow and the rest of it with Martin. So, digital 3D model is it software pattern or data pattern?
So it's a software plus data pattern, I think, because it's not just data, because data is inert.
So, can I make an example of the digital 3D model?
Yeah.
Simple one. Yeah. I think we can get it there. I think I like to draw something, so.
Yeah.
So this is digital 3D model of the cube. Yes. Actually, not this one. It's when we put it in computer.
Yeah.
So, how do you represent the cube?
You tell me.
There are a few different ways. One way is let's see if I can do this. 8. Oh, I need one. There's the GH. You need 2 more. 8. And what am I missing?
Okay, we can imagine the rest.
Yeah. So these are points.
Yeah. Good.
Or I can make, I can say I do have the 12 lines.
Yep.
Or I can have 8, 6 surfaces.
Yeah.
It depends. So
Okay.
any of them.
Yeah. So
These alternative ways. So I put these numbers and I interpret these numbers as a cube.
Yeah.
If I give number to Royu, he say, okay, just bunch of numbers.
Yeah.
I have interpretation of that model.
I
and
would
this
say-
is very software and data come together.
Yes. I would say that all of these representations of the cube that are used in CAD are going to be
They're going to be
they're
here.
going to be of the same cube within the
Yes.
software data
Yes.
of the CAD program as being realized in this particular computer or in any computer to which you send the data.
One more thing is, okay, for digital model, when we say operating part or part software, I've been talking about, there are 2 things. One thing is that when I'm making this CAD model, they are in operating memory. When I save my file, they go to disk.
Right.
There are two different SDCs.
Okay, and 2 different bearers because working memory and the memory.
And this working memory disk are 2 different pieces. Yes.
Yeah, but the very same cube is now being captured inside a single laptop in 2 different places. So we have 2 different bearers.
Yes.
That's the whole point of having generically dependent things.
Yeah.
The very same design can be in 2 different places, even within the same.
Yeah. When I open file, it exists in disk and it exists in memory, and I can go there. So that's.
And now something somewhat similar is going to apply, I imagine, to other kinds of industrial software artifacts.
I believe so. I mean, so there is complete theory here on how to represent this called geometric modeling, and this is where STEP is actually big on that one, and STEP NCB extension. So I do agree there are different things because, as I said, if you add this 8 times 4, 8 times 3, 54 numbers, and anybody can make maybe skewed a cube,
Yeah, right.
but anybody can make some cube. Some of them could be valid, some cannot be, could be actually shown not to be valid. If all of them are 0, 0, 0,
Yeah.
you don't get cube
And
anymore.
now how do you drill a hole in that cube? How do you design a hole in that cube?
Okay, so for hole, I need to have if I say, usually for hole, I do have to specify few things. One is a face on which I want to drill it. I have to specify depth, diameter. I specify type. And now what I'm telling you now is actually how CAD software works.
Yeah.
And if type blind, I have to specify depth.
And you have to specify the locus of the center point of the hole, assuming it's
Yes, a good point. And I have to specify point by Z when I start. I'm assuming here it's round hole.
Okay, it might be.
I mean, if it's square hole or something, it's kind of depends. Yeah, usually CAD software deals with the round holes. So point. Okay, this if I specify face, point is in 2 dimensions. I do have a reference point here on this face, and I specify point. I have diameter, and I have from type. Either if I go through, I'm there. If I have to break in between, again, if I am blind, this has to be smaller than this. Actually, some CAD software, if you specify blind and specify depth longer, they're still going to make it. Like basically, you specify blind, but they're going to make it true.
Good.
So you need 1, 2, 3, 4, 5 numbers, and then few references to specify whole.
So I don't think that CAD software breaks the BFO account of information entities.
I don't think so. So I mean, but that in this framework, this just becomes part of CAD model. I'm not changing, so I'm basically making this dynamic. I mean, going back to manufacturing process, no, it is not. This is actually design process. We have something similar. We do have input and we have output.
So let me take it to the next level. And now I have to remove your cube.
Yeah, no problem.
Then what we will do is we will move from continuance to occurrence. So how do we realize a piece of CAD design in not just in a product in the CAD sense, but in a product in the physical sense? So how do we make a cube? And the idea is that we have another information artifact, which is a production plan.
Yeah. Can you use plan process?
No, production. I need a production plan in order to have a planned process. You can only have a planned process if you have a plan. So you start with the plan, and you'll need software to transform. This will be the input. This will be the output, and then you have another digital artifact, which will be a piece of software. That's also an information entity, which will transform the input, which is the digital model, into a production plan. And of course, there'll be lots more input. There'll be material specification and so forth. And you also have to have...
Okay, just kind of, there is I mean, historically, a digital model design is only 3D model, but it's incomplete.
Yeah, of course.
Design has to include more.
Yeah, of course.
So I don't know. I don't think it's for me. Design includes material specification, tolerance specification.
Okay, so we have the 3D model as a purely geometric thing, and then we need a lot more to get the production plan. We also need specifications of the capabilities of the factory that's going to do the producing, for instance.
It's not part of design.
No, but we need it to have a production plan. There's a lot going on here. Yeah. So the production plan is also an information artifact. That's the point I'm making now. Yes. But it's an information artifact which contains references to lots of independent continuants, namely machines, buildings, sources of raw materials, and so on. Okay. And as contrasted with the digital 3D model, which doesn't refer to anything that's an independent continuum, just refers to it's abstract, in other words. Now we're moving into the concrete. And so this is about, so we haven't talked about aboutness, but the core relation in the ontology of information entities is aboutness. And this is just about something abstract. So we're not going to go into about geometry.
It's about something abstract because we didn't make it.
Yes. Because it can be made by many, many different kinds of processes. Okay. So it can become concrete in many different ways. And that aboutness of something abstract is something that we need to deal with separately. But now this production plan has an aboutness of many concrete things. This factory, these machines, this raw material, and so on. So this is about information content, independent continuance. It's a real production plan. There's a manager who knows it and who's going to use it to instruct.
If I just can interject here, because we go further. Usually in ERP world, enterprise resource planning, production plan refers to one particular thing, which is actually which product I have to make this.
So what I'm talking about the production plan.
I understand what you're talking about.
So let's say a generalized production plan.
Okay. What are you talking actually is information about factory. All necessary information which is not actually planned, which exists. It's not plan. This machine.
Oh, so no, but in order to create even a generalized production plan, which is about what's going to be made by this factory, you still need to refer to the factory and the
I have to
machine.
be fair. That's true. Yes.
But no, then we have more software which will turn and human input, which will turn this generalized production plan into a production plan for next week.